ya.
Awas, awas, awas.
Ini masih on kok.
Okay, because the time has passed around 4 minutes. Should we start the webinar right now? Ready? What do you think?
Monggo, boleh, silakan Mbak.
Okay, because the speaker also has another schedule after this. Okay. Allow me to open the webinar today. So, good. Sorry for that. Good afternoon to all the audience, and I suppose good morning, bonjour, Dr. David. I am Nurahmika Daryati, and I would like to welcome you to the 7th webinar series from Geological Engineering Department. Today we are so glad to have Dr. David Menier back with us as the speaker. So if you might have joined and follow the webinar series. On the previous series, Dr. David has delivered topics about stratigraphy and also coastal and marine geology. In case you would like to take another look back again, or maybe you missed and haven't joined the previous series, you can just kindly seek it in Geology Undip YouTube channel. Okay, as for today, Dr. David Menier will be delivering the topic about basic sequence stratigraphy. The presentation will be delivered in 90 minutes and continued by a question and answer session. So we highly encourage the participant here to have questions to Dr. Menier, because this is such a precious opportunity to have a discussion with him. For the audience, please do make sure to mute your microphone and turn off your speaker to prevent any inconvenience here. So yes, Dr. David, please, you may start your presentation.
Yeah, I'm just checking what is that. Did you see this? Okay.
I can see, but it's kind of a bit
Can I start?
lagging. Yeah, you can start now.
Okay. I don't know what is. Okay. Thank you so much. Thank you so much for your introductions. So by today, we will talk about sequences stratigraphy. I just want to tell to the students and all participants that I will send, and I have already sent to the moderator some documents that you will receive maybe later on in order to complete the discussions that we can have together. So what I propose, I will talk during 1 hour, and after that I will open the sessions, because I have only 1 hour and a half by today. So it's more shorter if you will compare with the last class. Okay, I don't know how I can move this. Did you see the title?
Yes, I can see the title, sequence
Okay,
stratigraphy.
because I have some. Okay, thank you. So sequences stratigraphy. So it's mostly developed by oil and gas company, and specifically from Geologist and from Exxon company. So Peter Vale and co-workers examine sequence boundary through the world, and they were trying to model all the architecture and distributions of sediment from the coast toward the abyssal plain. So using this type of model, so the more important thing that you have to care about that is to identify through seismic data the unconformity, like as you can see over there, with erosional surface passing to different surface, and sometimes without erosions, sometimes with erosions, and a concept about the architecture and geometry from coastal deposit to marine deposit, and related to the sea level rising, and in parallel to tectonic factors can affect the basin. So I will use that. So again, from this model, you can see that the sedimentary influx are very important as well in order to fill your basin, and you are trying to identify the most important controlling factors affecting the distributions of the sediment along the coast, or maybe into the basin that you would like to identify or understand the past dynamic. So sequence stratigraphy, has been developed in 1980. Even they were starting to have more concept in 1970, and identified genetic package and unconformity. So this is really important in order to provide a chronostratigraphic framework and trying to map the sedimentary facies and the stratigraphic predictions. So by today, we are still using these methods in order to develop the best understanding of the sedimentary basin in order to find where we can have oil, gas, etc. And by today, following what we have already teach about the coastal dynamics, so we are using same methods in order to identify unconformity, geometry of the sedimentary package, sedimentary facies, and trying to understand what are the result of this geometry, what is the result of the distributions. So it's quite a big revolutions when they were proposing that to sedimentologists around the world, because it was new and was a good help in order to define with a better understanding the architecture in the basin, in the sedimentary basin. So we need some definitions. So we need to use facies concept, integrations of lithology, fossils, and time. We have to know about a minimum of geomorphology, all the depositional environment that we can have. So I will recall some concept about that. We need to have in our mind a vertical sequence of facies. We need to know about progradations, aggradations, retrogradations, and of course, this is fundamental in order to build the block of stratigraphy sequences. Sedimentary facies, mostly it's very common, and we need to focus about first the lithological indicators, so grain size, and to identify what could be the main particles, what is the more abundant particle, is it quartz, is it fragment of shell, is it siliclastic deposit, is it carbonate deposit, and we have to identify that. In parallel, you have to identify the bedding, the presence of absence. Sometimes we cannot see the bedding, sometimes we can observe. So we can have as well at the outcrop scale good identifications about the presence of unconformity, the presence of cross bedding, the presence of oblique or parallel layers, something like that. So the bedding is related to the hydrodynamic processes. So this is the second thing that we can observe at the outcrop scale or using seismic data. And after that, if you have the chance to identify some biological indicators with fossils, macrofossil or microfossil, and of course the bioturbations affected the sediments, allowing to have a chance to define if we are nearby the coast or you are in the abyssal plain, if you have elements to define which type of depositional system where we are, if it's continental, if it's marine, or if it's between continental and marine deposit. So I have already give to the moderator, the best practice in sequencing stratigraphy for explorationists and reservoir engineer. So you will receive this book later after the talk. Again, so you know now my slide, one of the favorite slides that I want to share with you. And what I will do now, I will show to you some pictures of photography from glacial to abyssal plain, showing all the type of deposit that we can observe everywhere. And if we want to compare with the conceptual model built by Peter Vail, I mean this one, we need to have a good image in our mind following what we have here. So you can see the parallel about the framework, the parallel about the drawing, explaining what we can keep or observe in the sedimentary basin. And again, one of the objectives in order to have in order to use the sequences stratigraphy is to have the possibility to predict where are well preserved this type of sediment, this type of sedimentary package in my basin. So you can predict if you are in the continental domain or marine domain. So let me share with you some photos. So this is photos from the Monument Valley National Park in USA. You can observe over there some layers and some hills, and most of them were in the past in the same basin, so we can follow this unconformity and observe that the unconformity that we have on the left, we can observe in this strata the same surface. So the idea is to try to follow and to find all unconformities between two strata and to have the possibility to reconstruct, of course, the history of my basin. So in these pictures is to show that we can have a continuity from the left to the right, and we can go outside, see some outcrops, and to try to do, at least for the students, to have in their mind the possibility to follow all the strata. And if it's marine and it is continental, so it's quite difficult from the photo to do that. We have to work at this scale and try to identify the grain size, the lithology, the bedding, the stratigraphy, and of course to try to identify fossils or bioturbations. So as well, in my basin, for example, everywhere in the past, we have different type of deposit, and glacier can affect as well and transport some particles from the mountain to the sea or to the alluvial plain, and we can as well observe some type of deposit related to the glacier area. So it's a pictures as well that you can use for yourself and to see the glacier over there. And at the top here, you can see that the ice is not white, it's a little bit black or gray, showing that glacier can transport a lot of materials toward the valleys. Later on, or in parallel, in my basin, for example, I can have as well some alluvial fan or alluvial cone at the foot of my mountain. As you can see over there, you have a very huge lobe related to sediment supply from the mountain, and at the foot of this hill, and you are filling slowly the valley that we can observe over there. One more type of structures or type of landscape or features related to the alluvial plain. Over there, you can observe beautiful valleys with the rivers into the valleys. And on the left here, for example, in my landscape, I can observe a terrace. So you see the terrace over there, a terrace over there. So we know that the rivers can shift on the left, on the right. And in this case, in my basin as well, when I'm using seismic data in order to reconstruct the sequences stratigraphy, we can have sometimes some fluvial terrace. So it's an unconformity, and the rivers is shifting on the left over there. And we can imagine that in the seismic data, we can observe this unconformity. And this unconformity can be related to the sea level fall or rise, or maybe related to tectonics. So this is a rivers from New Zealand. So tectonics factors are really important and can affect the base level and can change and explain this type of valleys. Again, this is Brahmaputra rivers nearby Ganges deltas, and you see the huge plain as well, big rivers that you have in Asia, and Southeast Asia is very characteristic. So with a lot of sandy bank over there, so you can see the dynamics, and so it's very active, and from the mountain to where the Ganges and Brahmaputra Ganges deltas to Myanmar or Bangladesh country, you have this type of deposit that we can as well observe in the basin, because it's a huge and very large scales. Valleys is very wide, and imagine this type of sediment that we can observe in the basin. Again, if you go slowly and slowly to the coastline, this is Mississippi rivers. This is what we can observe, the channel, the present day channel, and on the left, on the right, over there, you can observe Oxbow Lake here again, here again. So my rivers is moving a lot, very quickly, shifting from the left to the right, and you can observe at these scales the moving, the progressions, the variations of the width of the valleys and the rivers. And it's one more feature that you can use and you have to put in your mind that you can observe as well in the basin with this type of huge rivers that we have everywhere around the world. So to be, to take time with you to try to understand what I'm trying to do, I'm sharing with you some photos, and all the photos are mostly from example that you can use by today, or you can collect from Google's or another server. Anyway, it's to have the capacity to compare with something that you know and can exist at the present day at the surface on our planet. One more image that we can observe over there, it's a lot of Oxbow Lake as well, with a lot of progradations over there. And this is the active rivers, active channel. And you see there, it's very complex, and you have a lot, so many sedimentary package on the left, on the right, and the channel can move very quickly and transport sedimentary particles. Anyway, this is vertical view, and from the vertical view, you can imagine the thickness of the deposit. And if we do a cross section from here to here, we can have a lot of paleo channel passing to a new channel. This one is no active and going to the active channel. And in this case, we are preserve a lot of sedimentary package with maybe clay, maybe silt, maybe sand, maybe gravel, etc. And for oil and gas company, it's really important to try to identify this type of deposit because we can predict where we have sand and where is the high porosity, high permeability in order to maybe collect oil and gas. One more example, so from Mongolia, between China and the front of Himalaya. So sometimes we can have rivers over there crossing the desert and with active sedimentary supply. And this is what we can observe there. So again, we have a very many difference, high variety or diversity of depositional system. This is really as well complex, and all the type of environment can be preserved in my basin. So let me show you one thing related to second stratigraphy. This is the Menier Basin in China Sea. And I would like to do a parallel between the Mississippi rivers with the channel that we have here, with concave and convex channel. And this is on the right image that we can collect from the Petronas company. And maybe you can collect from your national oil and gas company as well in Indonesia. Through your different basin, and you can see here an image showing as well a meandering system with concave, convex channel everywhere, and you can do the parallel with Mississippi rivers. This image come from Menier Basin, so it's like you are cutting, you can have a 3D block from a company because they are doing seismic data analysis, and they have a block with a 3D model, and you can go down your model, seismic model, and you can have the possibility to observe the type of environment, and you can recognize here some meandering system. But in this case, in this image, of course, we have a different one. So be careful with this image. It's a horizontal layers through a 3D block. But in this case, we can observe some channel, and we can do the parallel with what we have at the present day in the Mississippi. Meaning that if we have seismic data, and you have the possibility to have some 3D block, you can compare with present-day rivers, and you can interpret your image like your satellite image and propose a model where are located or preserved sand, clay, etc. Because you know that the company want to know that where are the best place where I can do a core or borehole in order to collect the oil, for example. Another pictures showing a photography from the Kinta Valley in peninsular Malaysia with the carbonate here and some artificial lake after the mining during the 19th century and 20th century. They have abandoned some place where they wanted to collect mine and some metals like tin metals, like in Indonesia that you are trying to collect now from the sea. That in my alluvial plain, I can have some lake as well, and with a small hill. So it's around 100 or 200 meter for the height here. So, and at the back, you have the backbone of peninsular Malaysia with the granite. Anyway, one more photos showing sometimes the complexity of all the landscape that we can have from the mountain to where the shoreline. And one more example, Great Lakes that we can observe by today between Canada and USA. Great Lakes have been formed during the last glacial maximum. After the melting of the ice, the fresh water goes toward the depressions and was filling the depressions topography. And we have by today a big lake, a very large one, in this area. When you are going toward the shoreline, we can build some deltas, like these deltas, Mississippi deltas, with different channel, very complex, and with some channel or canal, I don't know which term do you prefer, some channel impact or maintained by human infrastructures. Anyway, these deltas is progressing toward the Gulf of Mexico, and you can observe here some plume of sedimentary layers everywhere around the front of the deltas. And sediment supply is higher if you compare with some place around the world, and the Mississippi deltas continue to transport large volume of sediment, allowing to have this shape with this lobe, very complex, that we can study, and by today, very affected by the sea level rising. Sand coast or sandy coast, already shared with you last time, so we are going to do this. This is another type of landscape. We have the sandy zone over there. At the back, we have the marsh deposit and small place where we can observe some housing, and the coast can be as well occupied by a rocky place. Gulf of Mexico, but Gulf of Mexico is over there. Mexico is here, and on the left, on the western part, we have some strand plain deposit already described with you. So again, in my basin, I can observe maybe this type of deposit. Dune as well, and washover fan, maybe, if the definitions can be enough to see that with details. And we can as well have this type of deposit, tidal flat, or mangrove system, or maybe a barrier system, etc. So a lot of different depositional systems that we can preserve in this type of basin. And maybe if you have the chance, sometime we can preserve some rocky coast, but it's not mostly the case, because as I told you last time, rocky coast mostly is not well preserved. It's very rare to preserve that in the basin, because mostly and slowly, when the sea level is rising, you can erode the total cliff that we got previously along the coast. So I never see many examples showing, paleo rocky coast. So my experience, we have some example in USA, that's all. Carbonate platform as well that we can preserve in sedimentary basin, and we have a different model in sequence stratigraphy showing this type of deposit. Next class, I will share with you some seismic lines showing this type of deposit as well, in order to have this possibility to understand and to illustrate as well the concept, because the concept is interesting, but it's quite difficult to mature the concept if you are not using example. This is a carbonate platform that we can observe in the sedimentary basin. So I'm going, toward the sea now, and you can go to the alluvial plain from the continent. This is a Niger Delta place, and you are going toward the abyssal plain, and this is a basin 1, basin 2, basin 3, dominated by turbidite deposit. And turbidite deposit can go from the continental platform toward the shelf break with beautiful canyon go later on and with and transport sediment toward the abyssal plain, allowing to build some lobes like we can observe over there, that we call that deep sea fan. So in my previous photography, I just share with you some pictures from the mountain toward the deep sea fan, the abyssal plain, showing all the type of depositional system that we can record along this topography profile. And again, most of the factors explaining this type of the diversity of deposit is related to climates and tectonics, where we can have sometimes uplift or subsidence. This is the conclusions that I will propose for the first part. Okay, now let's go to sequences stratigraphy, reconstructions of geomorphology. So this is a 3D view. So from the alluvial plain, coastal plain, toward my marine basin. And which type of data we can use as well? If we don't have seismic data, we can have borehole data or core data, and we can, thanks to that, reconstruct with the sedimentary facies analysis the history of my landscape or basin. And we can identify over there coastal plain facies assemblage using microfossil or fossils. And when you are offshore, we can maybe observe some storm deposit or shoreline facies with shore face, lower shore face, upper shore face, or maybe the transitions between offshore and shore face. All the concepts that we have already explained last week. And again, so when you are doing the cross sections from the coastal plain toward the abyssal plain, in this case, you can see the progradations you see from the red layers or the yellow part over there or the blue one. This is offshore deposit, the blue, if you prefer, and the green could be the marsh deposit. And you can obtain a vertical sequences of facies through that. And if you do 1, 2, 3 borehole, you can reconstruct and propose this architecture, this 3D block. So you can reconstruct that, and all the surface, the limit that you have between the red and the yellow, or the yellow and the blue, this line is not time surface. This one is time surface. This one. This oblique or oblique line, this is the time surface. This one is only the separations between two types of sedimentary facies. Be careful with that. This is the limit of 2 strata, but this unconformity didn't correspond to the time scale. The time scale is this one. Okay. Okay, then when you have to define progradations, aggradations, and retrogradations. So progradations mean that you have a block, one, a second one, a third one, and the last one. And if the sea level is falling, for example, you can start the first one, and you go to toward the new base level. Could be related to the sea level rising. Aggradations on a flat surface mean that you have one more layers and one more layers. Sediment supply from the left here can explain that you have these aggradations. because you have enough sedimentary particles arriving from the left. So this is the difference between aggradations and progradations. So now we need to have in our mind the type of sequences that we can observe during progradations. So you can observe here that you have the continental surface over there, and you observe the progradations here. So this system is progradating, and you have aggradations over there. So during a progradations period, you can preserve the volume 1 here. And mostly during progradations, you don't preserve this part that you can observe in the continental domain. This is the difference between progradations period and retrogradations period. During this time, when the sea level is rising, for example, you can preserve the continental volume, and you are reworking a bit of the marine deposit that we were depositing here. So when we are thinking about sequences stratigraphy, sometimes you preserve marine deposit, sometimes you preserve continental deposit. And between marine and continental deposit, you have unconformity, where you have erosions or condensations. Okay? So this is important to have this type of model in your mind, and you can sometimes preserve continental deposit or marine deposit, and between of them you have a surface. It's an unconformity related in this case with the sea level rising. So these sediments from marine are reworked, and few of them are going toward or landward toward the coastal plain, and participating to the build of this is a tidal channel or sedimentary deposit that you can find in the mangrove system, for example. Okay, let's go. So one more so when we are talking about genetic units, the formations of genetic units in the alluvial environment, look about the stratigraphic log. So green, orange, blue, orange, green, red, green, etc. So we have different layers. So you know probably how you can trace a stratigraphic log. So this landscape sequences is showing what? You see between or during this time here, the authors of wood is showing an erosional surface. During this time, what is the landscape? During this time, my landscape is this one. I have a valleys with small tributary, and the main rivers is transporting or transport sedimentary particles, seawater, for example. And during this time, the main processes is erosions. We erode the top of the basement. That's why we have this erosional surface. And after that, during time, so from 1 to 3, we need time, and we have time, we are filling the rivers. And when the velocity of the water is decreasing, you fill with cross deposit. You see, you can observe black boulders and gravels. So the more cross deposit, and because they are they cannot be transported if the velocity is so slow, and they sink, they are sinking into the rivers. And you have some, you see that? You have some geometry. This is cross-bedding, showing the energy that you have in the rivers. And over there, we can observe some ripple marks, but asymmetric ripple marks in this unidirectional rivers. And you can observe the decreasing of the grain size. Anyway, parallel to the decreasing of the grain size, explain that the velocity of my rivers is decreasing. And you can see the second landscape that you fill the rivers with cross deposit, and in parallel, you are filling on the left, on the right, your landscape, and you can fill by maybe silt and clay or fine sand on the left, on the right. And you continue to fill your system. It's maybe what you can observe by today along the coast in Java, in the northern part. And you feel you have on the left, on the right of my rivers, some levee deposit in the yellow. And when you have, I don't know, the humid period, you can have some place where we can observe some lobe, because during the flooding system, you can observe overlay, and the water is going on the left, on the right, and you have some flooding, and you can have crevasse play over there. That we call that crevasse play. So new lobe. But the main rivers is over there. And you see in the red layers, so the cross deposit is showing these motions. So you can observe aggradational deposit from this period to this period. So this is important, that when you have a sedimentary facies, one sedimentary facies, it's related to one type of landscape. And sedimentary facies in the same place can change. And when the sedimentary facies change, you change as well your landscape. It's really important to put that in your mind, and always you are looking about sedimentary facies. You have to imagine what was my landscape during this time. I mean, what was as well my climate? What was the climate? It was humid or not, or it was dry? What about the rainfall? What about the season, etc.? And you have to play with that and to try to estimate what are the controlling factors explaining the difference. And you see, from the first stage to this one, you are feeling a lot, and you pass from marsh deposit to marsh deposit. And we call that a genetic unit. This is what you want to find in sequences stratigraphy in order to explain the reconstructions of my of the place that you want to study. What about the different sea level? Alors, relative sea level. Sea level measured from a reference point in the bedrock. Does not take into account sedimentary thickness, okay? Relative sea level is from the sea surface to the local datum. And you have sometimes accumulated sediment, and we call that from the sea surface to the top of accumulated deposit water depth. Water depth can change, as you know, and the relative sea level is always the same. The difference is the variations of the thickness of my sedimentary accumulations. Anyway, the different sea level can be dependent about different factors. The different sea level can be changed. So we have the water depth, we have the relative sea level, and we have the absolute sea level with the moon, for example, here. This is the example. Anyway, what are the consequences about the sea level change? This is more important to try to define in order to understand the type of geometry that I have well preserved in my basin. So during the geological scale time, we have relative change of sea level. It was high, it was low, high during, you see, around the time 500 million of years, so Paleozoic period, so Precambrian. So this is during the Paleozoic period, and so it's going down during the Permian, Triassic, Jurassic, and at the end of the Cretaceous period, you see the sea level rising and goes down after that till by today. This is at the large scales, and we call that the first order cycle. When we go with more details, we can observe another type of cycle, second order. So the first one is around 300 million years. The second one is around 10 to 80 million years. So you see the fluctuations that you can observe from Paleozoic period to Mesozoic period to where the Quaternary or Tertiary and Quaternary means Cenozoic period. So more you are going for details in your basin, you can, of course, see some fluctuations and affected as well the distributions of my sedimentary deposit. And at this different scale, when you are talking about causes, can be the plate tectonics motions, climate variations, or astronomical forcing, explaining this type of frequencies that we can observe in our depositional system during Paleozoic to Cenozoic period. Anyway, in order to illustrate for you the sequences stratigraphy, I think some sketch that you can use from online. So in the first stage here, you are during the period where the sea level is low, and you have incised valleys along at the foot of the mountain. So the depth of the valleys can be important, depend about the variations of the sea level change, depend about when the base level can decrease very rapidly or slowly. Anyway, sediment supply from the valleys can erode and explain the depth of my incised valleys over there. And in this context, we have the distributions or reworking of sediment. In the second stage, you see the sea level curve. The sea level is rising toward the land, and we build again here. We are building a barrier, sandy barrier. So it looks like same landscape that we have here, but you fill the system. If you have enough sediment from the land or from offshore, you can continue to during the this period to have a redistribution of deposit and go to this system with alluvial plain. Even the sea level is quite similar. You can see here or here it's quite similar, but you see in this case you are building deltas between this period or this one. What changed? Sediment supply, and you can observe some aggradations, progradations. So we have different type of sequences, and if the system is still in sea level, if the sea level is rising in this over there, this is what the case that we have here, and the sediment supply is very huge. You can see here the propagations of the sediment. So, and you are building the high stand system track. I will explain to you, sorry, because I didn't say that. We have HST high stand system track. We go to low stand system track, transgressive system track. I will use another picture to explain that. So you have that, after that, all the definitions of the term that we can find in this sketch. So the first one is failing stage system track that you can find now in different books. So it's formed entirely during the stage of relative sea level fall, forced regulations, and it occurs independently with ratio between sedimentation rate and accommodation space. This is one thing that is really important as well. You need space, you need accommodation space in order to preserve sediment. Okay, low stand system tract is formed during the sea level low stand and slow sea level rise when the rate of rise is lower than the sedimentations. This is the normal regressions. In the previous case here, forcing regressions can be sudden, affected, related to tectonism factors or maybe climate factors like we can observe during the Messian period around 5 million years ago, and in Southeast Asia is well observed, specifically in Borneo. Now, stand system tract that you need to know. Transgressive system tract, this is the sedimentary packaging that you can observe during the sea level rising, and the rate of rise is higher than the sedimentation rate. So it's like competitions, huh? And during this time you are going toward landward. And the high stand system tract is during the sea level is a little bit stabilized and the rate of rise is lower, and you can have the sedimentations along the coastal plain. So you can play with all these terms and go back to these pictures. So you see, high stand system tract, rate of sedimentations is higher than the sea level rising, and I can build a coastal plain. When during the transgressive system tract, the sea level rising is higher than the sediment supply, and you build a barrier over that. It's like the sediment is blocked along the coast, and from this period to this one, you filled over there. If you can observe with details, you filled the previous incised valleys that you have here. You see here, this sketch is this one. So this is where you can find maybe sand. Okay, so in the nature of the stratigraphic record. So go back to maybe more theory, sediment supply, stasis, and tectonism. And this is what we have over there. This is the accommodation space that we need in order to preserve and to try to understand the yellow package here. The yellow package is the same shape of sedimentary layers that I show you at the first scale from Peter Vale. And here you have 1, 2, 3 factors responsible of this architecture. Sea level can change vertically, tectonic with subsidence or uplift, and sediment supply can be related to climates or tectonics. So the concept of accommodations is the space available from sediment between the sea surface to the top of the basement. And again, these accommodations can change. So time and space scales of tectonics and stasis. tectonics, concept of tectonics wavelength, type of basin, can explain the shape of different basins that we can observe. And of course, depend about the plate tectonic motions. You have different type of basin, so it's very complex, and related to all the deformations that we can have after collisions or after subductions, something like that. Eustasy can be related to tectonic plates, plate tectonic, sorry, versus climates. Tectonostasis, sometimes you can change the sea level base related to tectonism. If the subsidence is very high or the uplift is high, you can shift and move the base level, and can be related exclusively with the climate. But mostly during the Earth history, it's related to tectonics and the climate mostly. So one more factor that Milankovic, it's a mathematics guy from Europe, described that is the precessions, obliquity, and eccentricity of the planets around the sun here. So sometimes the Earth's planet is describe elliptic curve and can pass to a circular motions. As you know, the planets can show is not true, or how I can say that there is an inclinations of the Earth's planets, and the planet is turning on itself, but describing a cone as we have here. So the climate is not the same during the Quaternary period, and was not the same during the Earth's history because of the orbital parameters variations. So we have tectonics, climates, and can be affected by as well orbital variations. So that's why we need to separate halocyclic control tectonics and statism related to Earth's formation, Wilson cycle, Earth's orbital parameters, and to separate to autocyclic controls, tide, storm, flows, and the timing is not the same. You see there you are more with million years or 10,000 years, but if you look about the processes related to tide or wave processes or storm, it's related to the years or maybe the second, etc. So we have to separate allocyclic control and autocyclic control. Okay, so what about now the shoreline geometry? In order to clarify the concept that we can use in sequence stratigraphy. What about progradations? Progradations can be forced, and you can have this type of shape. So you see the sea level is rising very quickly, for example, or related to tectonics. We can say progradations, pure progradations, and you can see the progradations, but this zone is relatively flat. We can have progradations plus aggradations, and we can have progradations, it's true, time 1, time 2, time 3, but you see the sediment supply is higher, and we can observe a subtle increasing of the thickness of sedimentary deposit along, for example, the coastline or the shoreline. You see the shoreline over there, so you can imagine shoreline, shoreline, shoreline tree. Aggradations is like that. You can just observe a geometry with aggradations and system, and the thickness with the rate can be the same or can change a bit. Retrogradations mean that the shoreline 1 was there, shoreline 2 here, and shoreline 3 is over there. So in order to learn, you can retrace this type of figures. After that, we go to shoreline geometry and the A over S cycle, mean accommodations over sedimentary flux. Sometimes we have enough space creations. And over there, you can observe a retrogradation system plus aggradations. So accommodations is superior to sedimentary flux. And during this time, you observe accredational and higher that you can observe accredation. Sorry, I'm a little bit confused. Accredations. So with this type of geometry, and you see again the geometry of the surface and the limit between different sedimentary facies. Second type, accredations. Accredations mean we have pure accredations over there. So this is maybe the shore face, surface, offshore, offshore, offshore. So we have a aggradational packaging. So this is, of course, theoretical. So, but anyway, it's to put different type of geometry that we can observe using seismic line. In this case, we have progradational plus aggradational system. And you can see the progradational and the sediment supply. It's sometimes important that we can have this type of geometry. When the equations, the divisions, accommodations over sedimentary flux is 0, we have pure progradations. And when is negative, we have forced progradations over there. You can play with that, and you can observe different type of geometry, different sedimentary geometry. Definitions about depositional sequences and stratigraphy cycle is defined as accommodations over sedimentary deposit variation cycle, mean all the cycle that we can observe and where we can observe progradations and retrogradations. So in the basin, using seismic, for example, you can see over there through the time, land wear on the left, sea wear. It's a model to try for you to reconstruct. You see, if you have in the seismic, you can observe this limit, this point that it could be the shoreline. You see the variations, and it's look like the sea level curve. This is what you can feel over there. In this case, you have creations of accommodation space. In this case as well, all the time. But the dilatations is not the same, and the time is maybe longer. But anyway, with the type of information that you got from the seismic, you can reconstruct, thanks to that, the sea level curve, and it's related to the basin subsidence, related to the tectonics. Mean that when you are looking about the stratigraphic records, we are talking about a stasi with different cycle plus tectonics. Mean that you can have different type of curve, but you combine both of them. Mean tectonic curve with the subsidence plus the sea level variations and during different time, and at the end you have this stratigraphic record with low or high, and you see the curve that you have over there. It's a curve showing the vertical variations that you can record in my basin. So you combine the sea level curve plus a tectonics level, but most of them depend about different time. So it's a little bit complex, but please just try to understand that for the moment, because you have to play with seismic, you have to train yourself in order to understand maybe that, but you try to do parallel with the sea level curve, and you see my sea level curve is reconstructed thanks to tectonic variations or climatic variations. Mean that with the theory, what we can do, if sometime you see over there the Stasi is low or high and see the same frequency and the same amplitude, we can sometimes have high tectonics period or low tectonic period, and the sediment supply can be low or high. Mean that this blue line plus red line can do this black line, plus the sediment supply curve can explain this type of paleo depth or paleo altitude that I can reconstruct during the time. I think that the time, the point, because when during the sea level falling or sea level rising, so you can preserve in the marine basin on the continental basin. So that's why you have at the end this paleo curve. So this is the additional of different factors when you are talking about the architecture of my sedimentary basin. Mean that what is the sea level? So the sea level it's fixed from the center of the Earth and the sea surface. And the sea level can be the water depth, the relative sea level if I want to discuss about what is occupied by sediment, or absolute sea level if I am estimated from the moon, or in order to see the vertical variations from only using the subsurface. Anyway, this is another case that showing subsidence rate and cycle geometry. This is the Stasi plus the subsidence with this type of subsidence, and this is the accommodation space that we can create. And sometimes during this period you can remove, sometimes you create something. If we have, and in this case you are in this context with passive margin or intracratonic basin, and when the subsidence rate is high, so it's like during in the geometric it's doing it's for example when you have a continental geodynamic context with rift for long basin or cyclic basin, you can create highest creations or lowest creations dependent about the Stasi curve plus subsidence. But you see the during this time you don't have maybe the same result, but anyway we know that in this geodynamic concept we have this type of curve that we can observe for accommodation period. Anyway, you can have high frequency cycle, and we have as well different order sequences that we can build, genetic units and parasequences. So this is a genetic units that we can observe. Progradations, retrogradations on the left. Progradations over there, retrogradations over there. I mean that when you are in the continental part or marine part, you in the 2D view, so you have to imagine that during this time, you remember I told you that this black line is the time scale. The limit here is the limit of by facies. So we have the coastal plain here, passing to the beaches, passing to the shore face, passing to the upper shore, offshore. So during this time, I build another sequences over there, the second one. And during this time, the sea level is falling. That's why I have this erosional surface. This is during this time that I start to erode and create incisor valleys on the continental plates. That's why I do that. And you continue to have the third sedimentary package, the fourth one, etc. The sea level is continue to fall during all this time. After that, stop. And you can observe during this time, maybe the sea level is rising again, and you have this deposit of marine deposit, and you start to build the coastal place dominated by coastal deposit with marsh or estuary or bay, etc. Bay, lagoon, estuary complex. So this is the genetic units that you can put in your mind, with the first part during the sea level falling. After that, it's the sea level falling stop. You build C, and C can be reworked during the sea level rising. And when we have sea level falling, we have progradational. We have progradations. When the sea level is rising, we are building transgressive system track, passing to retrogradation during this period, building the coastal plain deposit, and of course, maybe to have high sedimentations in my fluvial channel. What means ravinement surface? During the sea level rising or during the sea level falling, for example, you can change the wave processes. From T1 to T2, during time 1 to time 2, you see the erosions that we can observe over there. If and between time 1, 2, 3, and explaining that my barrier island is moving on the left, you build or you can observe this ravinement surface. A ravinement surface, in this case, is related to wave processes. Okay, and again, you can see here all the time scale or time surface 1, 2, 3, 1, 2, 3. When you have something on the left, on the continental zone, you have something on the right. But during this time, for 3, for example, you can see that in this space, the equivalent of my barrier is a ravinement surface. We don't have deposit over there. We don't have deposit. It's really important that sometimes we preserve sediment on the continental domain, but at the same time, on the surface, we have nothing. Maybe on the offshore part, we have some deposit, but I mean, it's comparisons that we need to know. Some definitions again. So the surface which corresponds to the most transgressive stratigraphic architecture marks the limit between genetic units and the useful correlations markers. So when you want to reconstruct the history of your basin, you have to try to identify the maximum regressive surface, the maximum flooding surface, using seismic data. And thanks to that, you have to use seismic line. And with the seismic line, this is what we are doing. We can observe the high stand system track, the low stand system track, and the transgressive system track. This is what I would like to share with you later, showing a seismic line and try to explain to you how we can observe that. So, in the concept of the Exxon schools from oil and gas company, they are proposing this type of model that they call that very famous slug model. from the continental place to the offshore zone. And we have unconformity, so erosional surface. We have incisions over there, erosional surface. We have the low stand system track, the transgressive system track, the high stand system track that we can follow using this black block. Black block, it could be, if you want, the shore face. And you can see as well that the trace here, down lap, top lap, etc., that I will explain later on. I recognize that next time I will show to you, and I will start with a seismic line because I think it's quite difficult maybe if you never used that before. Anyway, in order to work with that, we were using seismic data, offshore seismic, because with the offshore seismic that they got, they were illustrated the sedimentary deposit and the sequences. And they have the capacity with this seismic to predict the locations of the reservoir. They were looking about the low stand turbidite fine, etc. And secondly, they wanted to reconstruct the tectonic stratigraphic charts. Anyway, from that, what we can do? So how many timelines we can observe from the 1 point to the 2? So what we do, this is the time on the left, and this is the distance on the axis. What we can do, oh, sorry. Oh, I can see, okay. So what we can do, firstly, is to retrace all the line, 1, 2, 3, 4, 5, 6, etc. So all the line that we have here, 1, 2, 3. And I'm sorry because it was not, okay. Something is missing. How many lines? So, okay, it's directly like that. Sorry, I have a problem with my PowerPoint. Maybe you don't have this this line because I just added by today. So we put all the line. You see this one, for example, is come from here, and I try to reconstruct all. I retrace. Then I transfer all the line, and somewhere here we have sedimentations, and the blue part we don't have sedimentations. We call that hiatus. How I can use that? I'm just looking about the terminations of the line. And on the left here, we can call that on-lap. When it's like that, with a little bit oblique, it's down-lap. And when you are at the top here, we have top-lap. And we have some truncature. So I just passed through to this 3D, 2D model to 2D model, but I want to see where I have the place where I can find sediment. Because in this zone, we don't have sediment. And you know that the vertical line here is the time. And mean that if I am here during this time, I don't have deposit in this place. I am making or preserve sediment only in the offshore zone. So, and I'm trying to put in the vertical figures, I'm trying to put all the sediment. And this zone is shore face place. And somewhere we don't have sediment. So you can play with that. We call that Wheeler diagram. So I will play again. Look that. We have 35 lines. 35. And how do you trace line in the diagram? By projections. Okay. And you do that slowly and slowly. And after that, you can reconstruct all system track and measure unconformity in order to know where we have respective sedimentary deposit, where we don't have deposit, etc. In order to understand how was the history of my basin. And you have at the end the possibility to understand the Wheeler diagram that they were using in the oil and gas company. Okay, I will stop with that. So I will give back I want to open the questions because I have only already 12:30. I have only 10 minutes.
Okay, very well. That is the end of the presentation from Dr. David. Dr. David, we have several questions here, so I think we should make it quick.
Okay.
From Anis, Anis Kurniasi asked, how can we recognize the changes in sea level from deep marine facies? Because maybe considering that deep marine has the least impact of sea level change, right? So how can we define the boundaries in deep marine facies?
Yeah, that's why it's a good question. In order to define the boundary of a limit between this type of deposit, or you have to use borehole data or seismic data. So this is the tools that we are using about this. I will try to find. Let's see, a seismic line. Sorry, because it's very slow.
It's okay, take your time.
Could you see that, the seismic now?
I'm still seeing your okay, right now I
Okay.
can see your yes seismic.
Okay, so this is a seismic line in South China Sea. So to have the possibility to discriminate offshore deposit or deep deposit from coastal plain deposit from seismic line, we cannot define, but we can define after interpretation. So I don't have here the interpretations. Maybe it's a little bit difficult. This is what I can recognize. Okay. This is, for example, a seismic line with an example inside valleys. So this is granite. This is the bottom or the top of the granite. This is the incisions that you can observe over there.
Mm-hmm.
Okay. And here you can observe one more surface that you can have over there. It's like a small unconformity. And we have at the top another one, another surface here. So playing with the seismic, we can try to interpret that. And we know that after interpretations, that this shape is correspond to a channel, etc. But to be sure to know which type of deposit that we have, we need to have a borehole in order to collect the sample in order to identify the sedimentary facies. I don't know if I have already answered the question, because I recognize that now, next class, I will use seismic line in order to help people to understand. And I will use borehole data in order to show how we can do that, maybe.
Okay, yeah, because maybe this one is also seismic, also represent the deep sea, or maybe still on the coastal or shallow marine intervals.
Sorry, could you repeat the questions?
No, I was just highlighting that maybe the seismic section here has it already represent the deep sea, because I see it's cross cutting on the delta area.
This one is much better if you use that, for example. This is a basin. Okay, you can. Okay, let's see. I will use maybe surligneur. You see that?
Yep.
That.
Okay, so that is the...
Okay. This is the top. This is the basin, and we have some fault like that. Vertical fault. You see, you can see fault here, fault here, fault here. Okay. Could you see that?
Yep.
And here, you see here, you can feel the progradations. It's a deltas over there. But between this part and this one is not the same history. It's totally different.
True.
But I mean that over there, we have created accommodation space from the top of the basement, affected by fault. It's very complex, you see. We have a lot of fault everywhere, and we have the accommodation space here. 1 minute. Okay. No, because where I am by today, I have to leave because they are closing the door. Anyway.
Oh, okay.
Yeah.
I hope it's okay with you. I don't. We have.
No, it's okay.
We didn't
I
give
have
you...
I have 5 minutes. Yeah. What I will propose, because I prefer to stop. Could you send by email to me all the questions?
All the questions, yeah, because
Okay.
there are another lining question here on the chat box. Would you like to end the session right now, or?
What I will propose to the next class, I will start with the questions and I will show you different seismic lines that I want to interpret.
All right, very well. Okay.
Because I think that it was not the best to teach the theory without example from seismic. I think it's very difficult to understand. I just realized that when I was teaching, I said, oh my God, it's probably very difficult for the student to follow that. So what I will prepare for the last class on this Thursday, I will start again with small example that I want to share with you, and I will use the pointer in order to show. Okay? And I will come back with my slide in order to do the parallel. I prefer.
Okay, got it.
Okay?
Yeah. Okay. I think we are catching up with the time with David's schedule too. So yeah, audience, we have seen the presentation from Dr. David, the basics. So that is why it is given on the first before we going to on the applied things. So we can know some basic things that we have to understand first in order to create such an good interpretation using the tool of sequence stratigraphy, because sequence stratigraphy, even though it is quite a new theory, but it has been a powerful tool, especially very well known in the oil and gas industry, I guess. Yeah. So I would like to say thank you very much for your time. Merci beaucoup.
Thank you so much.
Merci beaucoup. I hope we didn't give you a hard time. I see you having a cold. I hope you get well soon. So
okay, Thank you so much. Terima kasih.
Terima kasih. So we would like to see you again in the next webinar series in a very better condition of you, and also in a very more interesting topics, of course. Thank you very much, David.
Thank you. Bye-bye.
Bye-bye. Terima kasih untuk para audiens. Yang demikian presentasi untuk webinar sore hari ini. Untuk dapat melengkapi materi yang hari ini, jangan lupa untuk mengikuti seri selanjutnya ya, yang webinar ke-8, karena itu rangkaiannya diatur sedemikian rupa supaya bisa berlanjut gitu ya. Untuk tadi seperti yang disampaikan oleh David, pertanyaan-pertanyaan yang belum terjawab akan saya kirimkan kepada beliau, dan nanti di webinar di awal presentasinya pada webinar selanjutnya beliau akan menjawab pertanyaan-pertanyaan tersebut ya. Pastikan sudah mengisi daftar kehadiran yang di-share oleh Ujenian, dan juga materi bisa di-download pada link yang sudah diberikan di chat box. Ya baik, oke. Demikian webinar series ke-7 dari Departemen Teknik Geologi Universitas Diponegoro. Terima kasih atas partisipasinya dalam webinar ini. Mudah-mudahan ilmu yang disampaikan bermanfaat dan dapat diteruskan juga kepada lingkungan sekitarnya juga. Oke. Apakah di sini ada yang mengikuti dari platform YouTube? Karena sekali lagi webinar ini juga disiarkan langsung melalui channel YouTube Geologi Undip. Dan bagi yang mau menyaksikan kembali, bisa disaksikan rekamannya pada kanal Undip Geologi, kemudian juga nanti, atau mungkin di sini ada yang baru mengikutinya, ya. Jadi materi-materi sebelumnya belum sempat dapat, bisa menyaksikannya di kanal Geologi Undip, gitu. Oke. Begitu. Terima kasih atas atensinya sekali lagi kepada para peserta. saya tutup webinar ke-7 pada sore hari ini. Semoga semua sehat selalu dan tidak bosan-bosan mengikuti rangkaian webinar kita yang selanjutnya. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera untuk semuanya.